Today we are going to continue with the How to Write an Operating System series. Seeing as my finals ended last night, I now have more time to actually think about this stuff and, devote time to editing and all that good stuff, albeit however little editing I do. So in this tutorial, or this part, you might recall, well, let's rephrase it this way, in last part, part 1, not part 1.5, you might recall that we were able, let me just open up a terminal, we were able to, write or print a character to a screen using a BIOS, and do the screen using a BIOS interrupt. So let me go over there. Okay, so if we go ahead and use QEMU to run our main, we see an X is printed on the screen right there. Whoops. And that's where we left off last time. So now we get to the point where we're wondering, okay, that's great, but if I have to go and, let's go into, if I have to use this sequence all the time to print a single character, so let's say I want to print out xylophone, starting with an X, then I have to move AL Y int 0x10 for every single character. Well, that's pretty inefficient. I mean, we're going to end up using a lot of space and a lot of time, and it's just inefficient in just about every way. So, is there a way around this? Can we write, say, like maybe a function that kind of does this stuff for us? And the answer to that is yes, we can. So to do that, well, first let me say that functions and labels are not so different from each other. So if you are familiar with like a language like BASIC, or if you do batch scripting, there are what are called labels. I don't remember if we talked about this last time or not, but if we did, I suppose you can kind of skip ahead. I'll just do this briefly. A label is like it's a flag in the code that kind of divides the code. So if you need to, you can jump to that piece of code. So if I have a label here, like say I do stuff, and then I have a label, and then I do more stuff. Up here, if I have some things I do, and in the middle of all of that, like as just have lines, I want to jump to my label, all I have to do is say call label, whoopsies, and then it will jump to my label. Now, with labels, since a label is a separator or a specific piece of code, like it identifies a specific piece of code, if that makes any sense. It's a position in your code. When you jump to that label, if you don't tell yourself to jump back, then it will just continue. So if you need to call or do stuff in that label, and you have more stuff you need to do after that, then if you don't have some sort of statement that tells you to jump back, you're just going to end up doing the label, and then you're going to go to the next piece, which in our case is hanging. So to fix that, you could say jump like back, and then create a label up here. But that's a little awkward. So instead of having to do that, assembly has given us the return command, RET, and that goes right back to where we were before when we called the label. So that then allows us to execute those lines of code. Now, because a label is not like a function, it doesn't execute when called. Only when called. If you have a label here, and even if you haven't called it, it happens to be the next thing in line, it will still execute. So, unless I have something that skips over this label, if I don't want to execute it twice, then I'm going to have to change my order here. And the easiest way to do that is to change where we jump, or where we have our hang function. So that way our labels are down here kind of below the main code, or the main area, so that we can call to our label, we do our stuff, we return back, and then we don't ever have to encounter the label again if we don't want to. So that way it's truly isolated. So we're going to do something like this for our print function. We're going to create a label or a function that prints out characters in a string. So to do that, we are going to instead rename this label to print, and we'll call it printf. We'll call it that. Okay. So now, because we're dealing with because our print function is a fairly temporary thing, and we don't want it changing things that we've already set up, we just want to print something out and then go back to exactly what we were doing, we are going to push everything to the stack using push A. And to keep in mind, push A is a command that you can only use in 16-bit real mode, but since that's where we happen to be, that's just fine. So we're going to push everything to the stack, and then we need to think about how are we going to do this. So what we want to do is have a loop that prints every single character in a string. So let's create a string loop. String loop. Oh, you can't have dashes. You can only have underscores. So string loop. Whoopsies. In labels, you can't have dashes or variables. So string loop. We're going to create that. And now we have to think about, okay, so where are we going to put our string? So what we can do is we can have, like, we can move our string to a register. So in this case, we'll say SI. We'll move it to register SI, and we'll have our string. Okay, and then you might be thinking, okay, well, that's great, but we haven't really defined our string. That is true. So to define our string, we'll come down here, and we will have a label that defines our string. So db, and then we'll say hello, whoopsies, world. Now, how will we know when we get to the end of our string? Because there could be instructions following our string. There might not be instructions following our string. How do we know when we've reached the end? Well, we can add to our hello world a 0. And what that does is that puts in a 0 byte right after our hello world string. So when we jump to this piece in code and load it into SI, we'll know that we've hit the end of our string when we hit a 0. Okay. So what we're going to do is we are going to move, and you might recall from our previous example, in order to print a character, we had to move the we had to move 0x0e into the high register, A high register, and then we had to move our character into the B, or the A low register, sorry. So, what we are going to do is we are going to move into our A low register our first character. Alright, because SI is that will load our first character, H. And this square bracket stuff, that is loading the address. That's loading a memory address of SI. So since we moved SI to this address, we're loading our hello world stuff over down here. Now we're going to compare AL to 0, so we can look for that 0 that we've put at the end of our thing. And if it is not equal to 0, so if there's still characters, we're going to print a character. And J and E says jump if not, means jump if not equal to. So print character, print char, char, whatever, is a loop, or a label that we now have to create. So before we do that, now if it does equal 0, that J and E print char is not going to execute. So we then need, when we hit that 0, that's the end of our string, so we need to return back to our main function. So in order to do that, we'll simply pop A, so pop everything from the stack, and then return back to our main our main piece of code where we called our print function. All right. Now we have print character. And then from here, we do everything that we did beforehand. So move to AH0x0E. And then because we've already set our A low bit, or our A low register, we don't need to do that again. Because, well, that's the whole point of the first part of the loop. So now we just need to call our BIOS interrupt. And then move our add 1 to our SI register to shift it so that when we look at when we treat it as a memory address, it shifts over 1. So that way we can look at the next character. So now we just need to add to SI 1, and then go back to string loop. So jump back to string loop. And that is our print function. So if we run this now, before we run it, let's just go through it. We haven't actually called the function yet, but let's just go through. Let's do that now. Call printf. So if we run this, we are going to be storing the memory location of str in register si. We're going to call printf, and when we do that, we're going to push everything to the stack so that we don't interfere with stuff that we don't need or that we don't want to. We're going to run through our string loop, and when we do that, we're going to move whatever is at the memory location of si, or what. Because SI is a memory location, when we put those square brackets around it, that means that it treats that as a memory location. So we're going to move whatever is at the memory location described by SI to AL. In this case, it's going to be our H. We're going to compare AL to 0, finding so that if we reach the end of our string, we'll hit a 0, and that's when we know we're done. If we're not done, for example, we see that H is not a 0, we're going to print character. So when we do that, we're going to move 0x0e to AH, we're going to call our BIOS interrupt, which will then print the H on the screen. We're going to add 1 to SI so as to increase or to move forward our memory location by 1, and then we're going to go back to string loop. So now SI is greater than it was before by 1, so we're looking at our E. Since E is not equal to 0, we'll do the whole thing over again, all the way down to D. So when we get to D, after we've printed out D, we're going to add 1 to SI, which will then make it so that SI reads the memory location of the 0. So when we move that to AL, we'll compare AL to 0, and we'll find that indeed they do equal each other. They are the same. 0 equals 0. And we will skip over this JNE print character because, well, they equal each other. JNE jumps only if not equal to. We'll pop everything from the register or from the stack back to, we'll pop everything from the stack, and then we will return back to this line here, only to run into our hang that will cause us to just infinitely hang there and not crash. So that's what should happen. So now if we compile our main to main dot whoopsies bin, and we run it, Oh. Alright, you know what, I figured it out. I think I did, at least here. Okay. So, something I forgot to mention. So when we're dealing with our boot sector here, we've got, let me just find an image for you. When we load our boot sector, there's a specific kind of map or layout that memory takes when you load a boot sector or you load an operating system. Okay? And as you can see, the boot sector is loaded into memory at, well, should be loaded into memory at 0x7c00, that address. So that those 512 bytes between 7c00 hex and 7e00 hex is the boot sector. Alright. We haven't specified that we want our boot sector to be loaded there. So when we're jumping to our memory location to print out our strings, it's not jumping to the correct place because we haven't specified where we want to be jumping from. We haven't specified, like, it's just kind of arbitrary. So to fix that, all we need to do is up here type in org 0x7c00, and what that does is it says load this code at 0x7c00 in memory. So now when we run this, NASM and QEMU, there we go, we get hello world, and that's what we should expect to get. So that was a little hiccup there. You have to remember to do that. I forgot about it, and I realized it eventually, but I did forget about it, and when you do that, then jumping to any place in memory is risky and not always guaranteed because you're jumping from an arbitrary location. So that is our print function, and that allows us to print strings uh, without having to type out those BIOS interrupts and stuff like that all the time. It basically created a loop for us. Now, another way to do this, I'm not going to type it in, but trust me that it works, is Assembly has this keyword command LODSB, and you could use this just the same, but to be honest, as we get further and further into our boot sector programming, especially if we get into 64-bit mode, into long mode, when we flip those bits in the CPU to transfer us to long mode so then we can start loading our kernel, we're going to be reaching our endpoint for the 512 bytes. We're going to be pushing it as far as space is concerned. So we're probably going to end up abandoning our print string function and simply printing out single character error codes that will allow us to debug what's going on that way. This does take up slightly less space, but in programming a 32-bit protected mode system, you're going to have a lot of space to work with, so it's not really going to be worth the extra couple bytes that you're going to be getting out of using this method versus the other. Not to mention the fact that I wanted to create a print string function using stuff that we've already talked about, so building on what we've talked about, and we haven't talked about this. We haven't talked about ORs yet, logical ORs, and looking at flags and stuff like that. So this was a little bit ahead of where we were, and so that's why I didn't use it. Anyway, that is how you print characters, strings, using a loop that prints individual characters. So next video we'll start talking about reading from a hard drive, a hard disk, and that will so that way we can eventually load our kernel from a hard disk into memory and execute it. So that's what we're going to be doing next. So be sure to join me for the next video in a little while. So, yep.